Okay. So today we have the first set of question is how to find the location of centroid and the inertia for a cross section. So for question 1, we have T section. We have a T section. This T section has dimension. Okay, this is our T section. The dimension of the T section are this one is 50, 25, 25. The heights are 50 millimeters the flange, 250 the width, and the dimension are 150 millimeter, 150 millimeter. Okay, and the vertical axis, y-axis here is axis of symmetry. This is y-axis, and x-axis is unknown for us because x-axis is not axis of symmetry, and the intersection of y-axis and x-axis is called centroid or center of gravity. CG. Okay, so the centroid or center of gravity is the location where the mass of this cross section is effective. Okay, and because this section is not symmetric about x-axis, so x-axis is not in the middle. Okay, the location of y-axis of the x-axis, sorry, is called y bar, which is y bar from bottom. You can assume it from bottom, y bar, or from top, whatever. But for this case, in this example, it is assumed from the bottom surface of the cross section. Okay. The first thing we need to know that for some cross section, before I start the solution, we have some regular cross section like rectangular section. So if we have a rectangular section B, the width with a dimension B in the width and H in the height. Okay. Do you know where will be the centroid of this section? Do you know? Because this section is symmetric cross section, so the centroid will be in the about x. X is symmetric axis, so x in the center. Y also is symmetric axis, so it will be in the center. Okay, so the centroid for this section will be somewhere here. Okay, can you just give me a second? Okay, so the centroid of the regular shapes, like rectangular, will be in the middle here. So the location of y bar or the location of centroid is here in the middle, y bar, and also x bar is here which is the location of the y-axis. So we don't need to know where is the centroid because it's already in the middle. Okay, and for centroid, we know where is the centroid. For the inertia Ix and Iy, the inertia is a physical term or physical property of the section or cross section, means second moment of area, or it's called moment of inertia. Okay, so this is a physical definition. This means that it is a probability of section of cross section responsible for resist bending moment. Okay, so this is one of the cross section probability which is responsible for resisting bending moment applied to the section. So if the section is under mx, so Ix is responsible to, or the ability of section to resist mx. Iy is the ability to resist my. Okay, so these two terms are some of the, or one of the properties of the material in about x direction or x axis. So Ix inertia about x axis, Iy inertia about y axis. From the definition, it means second moment of area. Second moment of area means the area multiplied by the distance or the lever arm squared. So A is area, Y is coordinate or location from the axis to the center of the area. This means that if you have any area, the inertia means the area multiplied by the distance from the CG of the area to the axis, which is called y squared. So I, the physical term, equal to A multiplied by y squared. Okay. This is the original definition, or how they get the formula for the energy. So for our case, I will remove this part. Okay, for the regular shape, we don't have to work out how they get the inertia, but we should know that Ix for rectangular shape equal to, so Ix is equal to B H cubed divided by 12. Okay, to keep in mind this formula, X here, so the first one is the parallel to X. So B is parallel to X, H is the perpendicular to X. So the inertia equal to the parallel to the axis multiplied by the perpendicular to the axis cubed. So if I ask you to do I, Y with same definition, so Y is the vertical axis. So what is the coordinate parallel to it, which is H? So H B cubed divided by 12. Okay, so H is the parallel to Y, B is the perpendicular to Y. Okay, so these two formulas, we need them to keep in mind for a rectangular section. Any rectangular section, again, Ix BH cubed divided by 12, Iy HB cubed divided by 12. Okay, so this is the inertia of a rectangular section. But there is a condition for these two inertia. The condition is this inertia is about x and y axis passing through CG. So if I am calculating the inertia of this section about this x-axis and y-axis passing through CG, so these two equations are applicable. Okay, for some cases, we have to calculate the inertia about axis not passing through the centroid. Okay, I will show you how can we find this. I will remove this part again. Okay, so for some cases, this is our section. This is B, this is H, and this is our X dash axis. So if I ask you to calculate Ix dash or Ix about X dash axis, do you know how to find this inertia? To find this inertia, we have the centroid of this area is somewhere here. This is the CG. This in the middle here, H divided by 2, H divided by 2, and here B divided by 2, B divided by 2. Okay? So to calculate this inertia, it is two terms. So the inertia, if the axis is not passing through the centroid, has two terms. The first term is the inertia about its own axis, which is B H cubed divided by 12. So if this is the x-axis, so the inertia is BH cubed divided by 12. The second term will be the area. We go back to the general definition of the inertia. It will be the area multiplied by the distance from the centroid to the new axis. So this is called y. So it will be A multiplied by y squared. Okay, so if the section the axis is not passing through the centroid of the cross section, this means that we have two terms. The term about its own axis plus area multiplied by distance squared. Okay, so don't forget that. So we have two general cases. We have case if the axis passing through the centroid and if the axis not passing through the centroid. Okay. Now, if we go back to our cross section, the T section, this always just some explanation for what we need to know in this type of examples. If we go back to our section here, now the requirement for this question is to find the centroid of the cross section, which is y bar. This is our first requirement. Second requirement is calculating Ixx for the whole section, or Ix for the whole section. Okay, how can we do this? Is the T section regular shape? Any one of you know where is the centroid or what is the I value for it? No, we don't know the centroid because it is not regular, it is irregular shape. And also we don't know the inertia because it is not regular shape. Okay, so what we have to do here, if we have any irregular shape, we have to subdivide it to some regular shapes. So what regular shape we can do here? We can do two rectangular. If I divide here, so we have A1, orange, and we have A2 in pink. So we have two areas, A1 and A2. These two areas are two rectangular, so we know where is their centroid and how much is the inertia for each section alone. So where is the centroid for each area? The centroid of area 1 will be here in the middle, so it will be in the middle of the 50 So it will be 25, 25. So this is the centroid for A1. Okay. And where is the centroid of the pink area? The centroid of the pink area will be in the middle here of the 250. So if this 250, so it will be 125 and 125. So this is the centroid for A2. So the first thing is subdivide the cross section to 2 or 3, whatever number of regular shapes. Then locate the centroid of each section. And we assume that the CG of the total area in the red circle here is somewhere between CGA1 and CGA2. Okay. And the location is defined by Y bar. Okay. To find Y bar, we have to do, or we have to use this formula, where Y bar equal to summation A Y divided by summation A. So this means that we have to multiply each area by its own coordinate, like A1, Y1, A2, Y2, and so on, divided by summation area A1 plus A2, and so on if we have more than 2 areas. Okay, so what is area? Area is the product of the width and length. What is Y? Y is the location from a reference axis. So the first thing we need to do is we will assume a reference axis to consider the dimension from. This axis I will call x naught. So this axis will be our reference axis. So because we know the distance here. Just remove this part. Okay, so we know here the distance from the centroid of area 1 to this axis is how do you know how much? We have 250 plus 25, so it will be 275 millimeter. Okay, and we also know where is the center of A2 from the reference axis. So this one will be 125. So we choose a reference axis because we know all the dimension from this reference axis to the centroids. Okay, so this will be our y's. So now using this formula, y bar will be A1. How much A1? A1 is 300 multiplied by 50. This is A1 multiplied by Y1, which is 275. I will write down here again. A1 is 300 times 50. Y1 equal to 275. A2 is 250 multiplied by 50. Y2 is 125. So we can do it outside or in the table or whatever, and then calculate the formula here. So we have plus A2 250 times 50. This is the area times the coordinate Y2, which is 125. Divide this over 300 times 50 plus 250 times 50. Okay. Using this formula, we can get that y bar is 206.6 millimeter. Okay. As you can see, where is this y bar from? This y bar is from the reference axis to the centroid. So this distance is 206.6. As you can see, the y bar is between y2 or the centroid of area 2, which is 125, and the centroid of area 1, which is 275. There's something between them. Okay. So this is the location of centroid for the total area. Okay. In some exams or in some questions, maybe the examiner asks you to calculate y bar from top. say here. So I will call it y bar 1. If I ask you how much y bar 1, can you get how much y bar 1? Because if you know the location from bottom, so you already know the location from top. The location from top will be 300 millimeter, the total height, minus 206.6 millimeter. This gives us 93.4 millimeter. Okay, so if the examiner asks you to calculate it from top or from bottom, it doesn't matter, but just you need to just know where you calculate from, and then you can subtract the total height minus the y bar from bottom, so you get y bar from top. Okay, so this is the first step, is to find the centroid, and now we finish the centroid location, and then the next step is to find ix. Do you have any idea about how much yx, or how to find yx? Ix, sorry, how to find ix? Okay, to find ix, ix is equal to summation the inertia for the subdivided areas. So in our case, how many areas we have? We have 2 areas, so it will be ix1 plus ix2. So if this our cross section, T section, this is our T section, and we know the dimension here, 50 to 150, and this one 50, and we have the axis here, x-axis and y-axis, and this our centroid. The location of the centroid we know already, it is 206.6 millimeter, and we have subdivided the areas to 2 areas. The first area is area 1, and we have second area, area 2. The centroid of area 1 here, the centroid of area 2 here. Centroid of area 2 was 175. Centroid of area 1 was 275 from bottom, and this one not 175, it is 125. Okay, this is the whole dimension we have calculated till now, and now we need to find ix1 and then ix2. I will do it separately to show you. So for ix1 equal to, how can we find ix1? ix1 is the inertia of this rectangular A1, and this is the centroid of A1, and we need to calculate the inertia about x-axis. That's why at the beginning of the session I told you that sometimes we need to calculate about axis not passing through the centroid of the area, because this x-axis is the centroid or the x-axis for whole section. So it is not passing through the centroid of the subdivided area. Okay? So what we need to do now is to find ix1 about this axis. So as I told you, ix1 about axis not passing through the centroid will be bh cubed divided by 12 plus a multiplied by distance squared. So this is will be our distance, and the area will be this one 50 millimeter, this 300 millimeter. Okay, so we know all the dimension except this dimension. Do you know how much this dimension is? Do you know how much this dimension is? This dimension from here will be this distance, which is 275 minus 206.6. Okay, so now to calculate ix1, we have ix1 equal to b, which is 300 times h, which is 50 cubed divided by 12. This is the first term, plus a, which is 300 times 50 times the area, the coordinate 275 minus 206.6 squared. Okay, so this is the inertia ix1. Okay, can you do the calculation for me? I will be in just a second. Okay, sorry guys. So now the calculation will be 350 squared cubed divided by 12. This will be, so ix1 will be 3.125 times 10 to the power 6. This is the first term, plus 300 times 50 times 275 minus 206.6 squared. This will be 7.70 point 1 70.17 times 10 to the power 6. So ix1 in total will be 23.3 times 10 to the power 6 millimeter to the power 4. Okay, the unit for inertia is millimeter to the power 4. Why millimeter to the power 4? Because ix, the unit is b, which is in millimeter, h cubed, which is millimeter to the power 3. So the unit will be millimeter to the power 4. Okay, and also for the second term, a times y squared, a will be in millimeter squared, and y in millimeter squared, so it will be millimeter to the power 4. Okay, okay, thank you, Tian. So this is the first term of inertia ix1. Now, if we want to do the second term of the inertia ix2, with same concept, ix2 will be, if we take this area outside here, this is the area, this dimension is 50, this dimension is 250. And the centroid here is at 125 millimeter, and this is the axis, x-axis, and this was 206 millimeter. So again, the centroid of the total area not passing or x-axis not passing through the centroid of area at A2. So we have two terms. It will be BH cubed plus A times Y squared. So for this area, B is the parallel to X, which is 50. H is the perpendicular to X is 250 cubed. This is the first term. The second term is the area 50 times 250. This is the area time. How much is this distance or this dimension? It is 206.6 minus 125. So y in this case will be 206.6 minus 125 squared. So if we do this calculation, 50 times 250 to the power 3 divided by 12, this gives us 65.1 times 10 to the power 6. The second term is 50 times 250 times 206.6 minus 125 squared give us 83 times 23 10 to the power 6. So finally, Ix2 will be 148 times 0.33 times 10 to the power 6 millimeter to the power 4. And finally, Ix for the whole section will be Ix will be 73.3 times 10 to the power 6 plus 14833 times 10 to the power 6. Okay, these two values together give us the final value of the inertia is 2.21 times 10 to the power 6 millimeter to the power 4. And this is the inertia. Okay, do you have any problem with this one? Okay, no problem with this one. Okay, that's good. So now we finish the first part of the tutorial, and we will stop sharing now. And now we'll open the second part. The second part today is the bending stresses or normal stresses due to bending. So I will share the screen with you now. So I will ask you to find the inertia for this two section, please, and give you 10 minutes to do this. Because this question, we need to calculate the stresses, but the stresses include the calculation of the centroid and the inertia. So please calculate the centroid and the inertia for this two section, and I will give you 10 to 15 minutes to do this, and then I will continue with you. Okay? Okay, only 10 minutes to do this. Thank you. Okay, guys, have you finished? Have you find the value of Ix for the two section or two cross sections? Okay, I will start doing this question now. So for the second part of our tutorial, we are doing the bending normal stresses. And I will share the other screen now. So yeah, we will do the bending normal stresses, or we can call it normal stresses due to bending moment. Okay, the normal stress due to bending moment, we give it the symbol sigma. So we have sigma x because most of the moment will be mx. So if the moment mx, so the stress due to this moment will be sigma x. Okay, sigma x can be determined using the formula mx divided by ix multiplied by y. Okay, so generally, if we have a cross section like this, and we have moment applied on this, we have moment applied on this cross section, mx. This moment called mx because it is rotating about x. So mx rotating about x axis. So the stress due to mx equal to mx. Mx is the bending moment about x axis. Ix is the inertia or the moment of inertia. We just calculate in the first part of the tutorial. Inertia about x axis. What is y? Y is the location of the point of calculation. What does this mean? This means that you can calculate the stress at point 1. So what is y? This is y, y1. Let's say here you want to calculate the stress here at point 2. So this is y2. So what is y? Y is the location of the point of calculation from the centroid. Okay, so from the centroid CG to the point, this is y. Okay, so if you want to calculate the normal stress sigma x, it will be the moment mx divided by the inertia ix multiplied by y. So if you want to calculate the stress of a cross section, you need to know ix. So for some problems or in the exam, maybe the examiner don't ask you where is the centroid or what is the inertia of this cross section, because you will have to calculate it yourself to find the normal stresses. Okay. So now we know the general formula for the stress, and we now can start our question or solving our question. So for this question 1, we have two consideration of a beam design, and the applied moment mx equal to 150 kilonewton meter. So the first information that mx equal to 150. The requirement is to find sigma x max, to find the maximum stress for the two section and choose which one is more effective. Okay, so I will divide the screen to two parts. We have two cross section. The first cross section here is I section. Both are I section, but one with increased web and one with increased flange section. So if this our web, sorry, this our flange, and this our flange, bottom and top flange, and we have the web. Okay, the dimension are the width of the web of the flange 200, the depth is 15, and the web height is 300, and this flange is 1500. So this is the dimension we have, and the web width is 30 millimeter. Okay, so now the first step is to find the centroid. Do we need to do any calculation to find the centroid? No, because the centroid is already known in the middle, because y axis is axis of symmetry, so this is y axis. X axis also is axis of symmetry, so this is x axis, and the centroid is here. So this is our CG. Okay. The next step is to find IX. To find IX, we need to subdivide the section to some regular shapes that we know. So we have this one is the flange. I will give it A1. And because the flange is identical, so A1 and A1. The centroid of A1 in the middle here, centroid of A1 in the middle here. This is 7.5 and 7.5 here also. 7.5, 7.5. Okay. And we have A2, which is the web. Okay, so this web is A2. Where is the centroid of the web? In the middle here. So the centroid of the web coincides with the centroid of the whole section. Okay. So now, if you want to calculate the inertia Ix will be Ix1 multiplied by 2 plus Ix2. Why? Why we have Ix1 multiplied by 2? Because we have two flanges. So you calculate for one flange and multiply by 2 because they are identical. So we don't have to calculate for X1 for A1 twice. Okay. Now Ix in one line, I will calculate it in one line, will be Ix1, 2 in Ix1. The centroid or x-axis not passing through the centroid, so we have two terms. The first term is the parallel to x, which is 200 times the perpendicular to x, 15 cubed, plus area. Area is the product of these two. So we have 200 times 15. This is the area times how much is the distance from the centroid to the centroid of the whole section. This half, this 300 divided to two halves, so 150, 150. So the distance from the centroid of A1 to the centroid of the whole section is 157.5 millimeters. So the distance here is 157.5. Don't forget the square. Plus Ix2. Ix2, because the centroid of the area coincides with the centroid of the total of the whole section. So we have only one term, which is BH cubed divided by 12. So we have 30 times 300 cubed divided by 2. And the other term is 0 because the centroid is same no distance between the centroid and the x-axis. So finally, we can get that Ix will be 148.95 times 10 to the power 6. This is the first part, plus 67.5 times 10 to the power 6. So this is Ix2, and this I2 from Ix1. So the final inertia will be 216.45 times 10 to the power 6 millimeter to the power 4. Okay, this is the inertia for the first section. The second section is with increased flanges. So the flange is double. So this is the cross section. So we have the dimension here is 30, 30, and 300 millimeter. And we have here 200 millimeter. Okay, the thickness of the web is 15 millimeter. Okay, so for section 2, the centroid also is known because the section is symmetric. So x-axis will be in the middle here, y-axis will be in the middle here. So this will be our CG for the whole section. We need to subdivide the section to 3 areas or 2 areas because the 2 flanges are identical. So we have A1, A1, and we have A2. Okay, so for the inertia, Ix will be 2Ix1 plus Ix2. So for Ix1, the inertia will be, where is the centroid of Ix1 of area 1? The centroid of area 1 is here. So it is far from the x-axis for the whole section. This one in the middle, so 15, 15. So this will be 165 millimeter. Okay, and also this will be 15, 15, and this total is 300, so 150, 150. Okay, so the inertia Ix1 will be about its own axis, 200 times 30 cubed divided by 12 plus the area, 200 times 30 times the distance squared. So it will be 165 from the centroid to the centroid of the whole section. Plus for Ix2, again, the centroid here of the total area is coincident with the centroid of the area A2. So the inertia Ix2 will be about its own axis, 15 times 300 cubed divided by 12 plus 0 because no distance between the centroid and x-axis. So from this equation, we find that, from this formula, we find that Ix will be, the first term will be 200 times 30 cubed divided by 12 plus 200 times 30 times 165 squared and 2 will be 3 point will be 327.6 times 10 to the power 6. This is the first part plus 15 times 300 divided by 12 plus 33.75 times 10 to the power 6. So the total inertia will be 361.35 times 10 to the power 6 millimeter to the power 4. Okay, so which one got a high inertia or bigger inertia? So the inertia of section 1 is smaller than the inertia of section 2. So which section is more effective or more stronger? So section 2 is more efficient or effective or stronger than section 2. Section 1, sorry. So section 2 is more effective than section 1. Okay, section 2 is more effective. So this is the first part, is to find the inertia and know which one is more effective. The second part is to find the stresses. So now I will write down the inertia to use in the next slide. So we have 14. So now we have for section 1, Ix1 equal to Ix section 1, so section 1, 261 point, sorry, 216.45 times 10 to the power 6 millimeter to the power 4. Ix2 for section 2 equal to 361.35 times 10 to the power 6 millimeter to the power 4. This is the cross section with the dimension. And this is 15, 150, 30, 200. And we have the centroid in the middle here. So this is X, this is Y. Okay, and the second section is thirty, 300, 200, 50. And the centroid is here. In the middle. So now we need to calculate the maximum stresses for each section. So sigma x max will be mx divided by ix times y. Okay, given in the example in the head, mx equal to 150 kilonewton meter. Okay, the best unit to use for calculating the stresses here is to use Newton and millimeter. This is the best unit we need to use. So how to convert from kilonewton millimeter to Newton millimeter? To convert from kilonewton to Newton, we need to multiply by 1000. To convert from meter to millimeter, we need to multiply by 1000. So from kilonewton meter to Newton millimeter, we need to multiply by 10 to the power 6. So if we have mx 150 kilonewton meter, this means it is 150 times 10 to the power 6 Newton millimeter. Okay. So now, if we substitute in this equation, sigma x max equal to mx 150 times 10 to the power 6 divided by 216.45 times 10 to the power 6 times y. here Y will control the maximum stress. Because for each section, Mx and Ix are constant. So which point has the maximum stresses? The point of maximum stress will be the farthest point from the centroid. So we have if this any point here on this line will be the farthest distance from top. And also similarly, we have the first point will be here in the bottom. Any point here will be sigma, will give us maximum stress. So we have Y max top and Y max bottom. Okay, Y max here will be 150. This is 300. So it will be 150 here. Okay, so the maximum value, sorry, the half of this distance is 150. So the maximum value or the location of maximum stress will be 150 plus 15 will be 165. So Y max here will be 165. So from this calculation, we can find that sigma max will be 150 divided by 216.45 times 165. So this gives us sigma x 114.34 Newton per millimeter square. Okay, why the stress unit is Newton per millimeter square? Because when we substitute in sigma equal to the moment, we use Newton times millimeter divided by the inertia in millimeter to the power 4 times y in millimeter. So millimeter and millimeter go with the power 4 and make it millimeter to the power 2. So the unit of stresses is Newton per millimeter squared, which is equivalent to megapascal. So megapascal is equivalent to MPa, equivalent to Newton per millimeter squared. Okay, so this for section 1. For section 2, we will do same things. So sigma x max for section 2 will be mx ix times y max. Sigma x will be mx, which is 150 times 10 to the power 6, divided by the inertia of this section is 361.35 times 10 to the power 6 times y max. How much y max here? Here again, this distance is 150. So the maximum will be at the top, any point on the top here, which is 180 millimeter from top or 180 millimeter from bottom. So y here is 180 millimeter. If we do this calculation, sigma x max for section 2, and this for section 1, for section 2 will be 150 times 180 divided by 361.35 E6 will be 74.71 times 10 to the power 6. What is the unit of stress? Newton per millimeter square. This is the stress. If we have a look on the two stresses here, we have 114 and 74. Sorry, there is no. We have here 114 and 74. So if we have a look here, the stress, the maximum stress on section 1 equal to 114 MPa is larger than sigma x max for section 2, which is 74 MPa. So which one is more effective? We already got it from the inertia, but now again from stress. It is better for us for the section to have less stresses, because less stresses mean it is safe. If you have large stresses, this means maybe exceeding the material limit and it will fail. So section 2 again is more effective than section 1. Okay. So this problem was to find how to find the stress, maximum stress for each section, and pick the more effective one. So section 2 was more effective for us according to our calculation. Okay. Do you have any question for this one? You have any question? Okay, thank you. Now I will give you some time to do the second problem here. This one, the same idea. So I will give you some time to do it.